Okay, so yeah, thanks Benjamin, and let me thank the organizer for giving me the chance to be here and present this work, which forms part of the activities of the research project Seaflower, which is a Marie Curie research individual fellowship research project that I carried out, as said, with the collaboration of University of Western Australia with Christophe and Phil and Tian from Melbourne, and under the supervision of Laura at Unibo. The study is about the effect of the spatial variability in the response of plate anchors, particularly looking to the inertial capacity. So let's give me an introduction to the topic. It is well known that the undrained capacity of deeply embedded plate anchors in homogeneous clay can be assessed using the capacity envelope approach, and also true that probabilistic failure envelopes are being proposed, and it has been proved that the soil heterogeneity in the undrained shear strength can significantly affect the uniaxial capacities, which in turn govern the size of the envelope rather than the shape. And in terms of design, typically there are papers which are proposing charts to allow the size and the shape of these probabilistic failure envelopes to be defined for distinct level of their probability of occurrence, but these methods are typically given for deterministic combination of the input variables which are governing the generation of the random field. So given these, the aim of this study was to develop a generalized approach to assess the statistical distribution in the uniaxial capacities, and it has been done through the definition of an operative undrained shear strength, as shown in the following slides, and also the computational cost of the procedure has been optimized via a surrogate model. First, just to understand a little bit how it works, the generation of non-stationary random field, as in this case, the input parameters which are governing this generation are first the two parameters of the trend function, so the undrained shear strength at the midline and the gradient of the curve, and then we have three parameters which are governing defining the space variability, which are the two scale of fluctuation in the vertical and horizontal direction and the coefficient of variation of the undrained shear strength. Now in this study, we set the undrained shear strength of the midline nearly equal to 0, and the horizontal scale of fluctuation set to be 10 times the vertical one, whereas the other three input variables are randomly varied within the ranges of variation reported in the slide. Now, I'm not going into the details on the generation of the field. I give you the chance to check the paper for the details. I have just highlighted here how the three the different input parameters enter into the realization of the random fields, and specifically the coefficient of variation and the scale of fluctuation into the definition of the stationary random field, and then the gradient of the trend function is inherently implemented into the trend function itself. So some example of spatial fields of SU generated by randomly varying the input variables, and also looking at the area just around the plate, we can see the high variability of the undrained shear strength that can be obtained. So those random realization have been implemented into finite element models with considering three different widths of the anchor, from 1 to 4 meters, Tresca soil as for the failure criteria, and displacement control simulation to analyze the ultimate capacities. For each anchor width, we have selected 10 ramput combination of the input variables, and then for each combination, 10 random fields were generated. So it means 300 simulation for analyzing the capacities, which were interpreted as standard in the literature by using the undrained shear strength at the anchor reference point, which is deriving from the trend function. And here the interpretation of the result, and you can see that the capacity factors are really varying, spreading between wide ranges of variation, which is consistent also with observation in the literature. So then after that we stopped and we checked a little bit how it was working the failure mechanism, and here I showed you in the first 3 columns the typical failure sum of the failure mechanism that can be obtained in random fields, whereas in the last column you can see the typical kinematic failure mechanism for homogeneous material. So it is true that there are variation, of course, it is well known there are variation considering the random realization, but as a first attempt, let's say, we had tried to use the shape of the kinematic failure mechanism of uniform material for computing this mean value of the end range shear strength, which is considering all the cell elements crossed by the failure planes. And in particular in this case, for just a random combination of these three input parameters generating the fields, I have reported the distribution of these three values of the end range shear strength and fitted them with a log normal distribution, which is characterized by a scale and the shape parameter. And a couple of observations on that is that first, if you set the scale parameter is nearly equal to 1, so we set it equal to 1, and the distribution showed by the black curve is not varying a lot. And the second is that the shape parameter is nearly, they are very similar for the three distribution. And indeed, considering a mean value of the end range shear strength, the distribution, the best fit distribution set with a shape parameter which is very close. And it has been proved, show it here for other couple of input combinations just to demonstrate it is consistent and valid. And so we use this operative end range shear strength for analyzing the data. And that's what happened to the FE data we have seen before. You can see that now the distribution is nearly close to a constant value. And indeed, even zooming, we can see that we can assume a nearly constant value for the three capacity factor by using this operative end range shear strength. So this opened the door to this application of a generalized approach. And in particular, we use the regression method through a metamodel, polynomial chaos metamodel approach for just having a regression of the shape parameter of the operative end range shear strength. So we have the three input variables which are generating the fields, and output of interest is the shape parameter. And I'm not going in details on that. You can just see in the plot the validation of this surrogate model, which clearly, it is clearly fine for analyzing this data. And so now I'm moving to show you what is the mean of all of these. We thought about three different methodologies which can be approached for analyzing a problem. Let's start by a standard approach where you estimate input variables coming from site information. You can have information about the gradient of the trend function, the scale of fluctuation, coefficient of variation. And so then you generate a certain number of random fields. You implement them into a finite element model, you run the simulation, analyze the data, and you can extract relevant statistics of the capacities. But this is time consuming in terms of generation of the fields and also for the FE simulation. So a second methodology could be to, skipping out the time cost for the simulation, because after generation of the fields, I can compute the operative end range shear strength and finding out the best fit shape parameter and analyze and then scale to the distribution of the uniaxial capacity through the bearing factors, the capacity factor, sorry. And then in the last method, we also skip the cost in terms of time for, and complexity also, I would say, for the generation of the fields, as we can use the equation of the surrogate models to compute the shape parameter of the operative end range shear strength and then scale the distribution again. So I try to give you an example. I considered a width of an anchor of 1 meter subjected to pull out and for the three input variables reported here. And they were generated 300 fields, run the simulations, and plot the distribution with a log, the distribution fitted by a shape parameter of 0.247. And then applying the second method after generation of the fields, it was computed the end range shear strength, and the best fit shape parameter was 0.254, and it was then scaled to the distribution of the vertical capacity through the constant value of the capacity factor here assumed equal to 11.8. And in the last plot, we simply applied the polynomial chaos equation with the three input variables for computing the shape parameter and then scaling. And you can see that the three distributions reported in curves with different colors are very similar to each other, just so demonstrating the validity of the approach. So in conclusion, a generalized approach has been proposed and I would say validated on three different anchor geometries. This approach is valid for any random combination of the three input variables which are generating the random realization. And this random realization, it has been demonstrated it can be associated to an operative and range shear strength, which supports single values of the capacity factor. And yeah, in conclusion, it is possible to relate the statistical distribution of the operative and range shear strength to the probability of failure of the plate under uniaxial loading, just using some equation without having to run computationally expensive analysis. And that's all. Thank you.
Thank you. We have a couple of questions. Question one, how random is the simulator? If it runs a million times, would it give the normal distribution or any other one?
Probably you can fit it also with other kind of distribution, but for I would say that the log normal distribution was perfectly working in this case. So, I mean, looking at the data with 300 simulation, but even increasing, I tried to increase the sample, even using a larger amount. I arrived up to about 1,000, and it was more or less the same, the kind of distribution. So,
how this approach could be adapted to other foundation types, please?
How can, sorry, be adapted?
How can we adapt your approach to other foundation type? Do you know?
Well, at the moment we have tried only for this plate anchor solution. I think that at the end